Okay, in this video we are looking at exponential functions. An exponential function is of the form f of x is some number a times b to the x. This is our basic graph. We'll be taking this and shifting it up, down, left, right, whatever. A here is the initial amount. B is called the base. Couple of restrictions. A is not allowed to be 0, because if A is 0, I get f of x equals 0, which is just y equals 0, a horizontal line. That's not an exponential function. B is not allowed to be negative. We can't have a negative base. B has to be positive, but it's not allowed to be 1. Because if b equals 1, anything, or 1 to any power is always 1, so we would just get y equals a, another line, which is not an exponential function. Okay, so here are our restrictions. We're allowed to have positive or negative a's here, just can't be 0. B here, the base, can be any number that's positive, not equal to 1. If a is positive, and b is bigger than 1, we get a graph that will look something like this. Pass through the point 0a, our initial amount. That's our y-intercept, 0a. This is going up, you can see. We call this exponential growth, because it's growing. It's an increasing function. And it's increasing for all x values, negative infinity to infinity. Our domain is all real numbers, negative infinity to infinity. Our range, the y values we use. Well, this thing, if you look going backwards, it's getting closer and closer to the y-axis, but never actually hits it. So we're only using positive y values. Our range is 0 to infinity, with the parenthesis here. And we have a horizontal asymptote, y equals 0. The graph gets closer and closer to the line y equals 0, but never hits it. If, on the other hand, say again a is positive, but b is between 0 and 1, if we have a b like 1/2, 1/3, then we get a graph that goes down, still passes through the point 0a, the initial amount. We call this exponential decay. So, radioactive substances follow exponential decay. Bacteria in a petri dish, any kind of population will follow exponential growth. So this graph is decreasing, negative infinity to infinity, same domain and range. Domain's all real numbers, range 0 to infinity. And we still have a horizontal asymptote, y equals 0. So it's b that determines whether you have growth or decay. If b is bigger than 1, you have growth. If b is less than 1, and still positive, we have decay. Okay, an example. Let's look at f of x is 2 to the x. So here, the number in front, a, is 1, because there's nothing here. This is 1 times 2 to the x. And our base, b, is 2. Okay, let's make an xy chart for fun. So let's make up a bunch of x's, find the y's that go with them, and plot them. If x is 0, 2 to the 0 power, anything to the 0 power is 1. Hey, look, that's our initial amount. That's what A means. If you plug in 0, what's your output? How much are you starting with? If I plug in a 1, 2 to the first is 2. If I plug in a 2, 2 squared is 4. If I plug in a 3, 2 to the third is 8. Okay, what about some negatives? Let's plug in some negatives. Negative 1. Domain's all real numbers. I can pick any x value I want. 2 to the negative 1 power means, remember what negative exponents mean? Means flip it over, that's 1 over 2. What about negative 2? 2 to the negative 2 power means 1 over 2 squared. 2 squared is 4, so 1/4. Hey, seeing a pattern here? Negative 3. 2 to the negative 3rd power means 1 over 2 to the 3rd, which is 1/8. Okay, let's graph this. Just a quick sketch. Okay, so we've got point 0, 1, the point 1, 2, the point 2, 4, the point 3, 8, 5, 6, 7, 8, and so forth. Notice every time I go over 1, I double the output because that's the function. And then going backwards, we just kind of have to eyeball these. We get a half at negative 2, a quarter at negative 3, an eighth. We get some graph that looks roughly like that. There's f of x equals 2 to the x. A is 1, my initial amount. My y-intercept is the point 0, 1. B is 2, that's bigger than 1, so we have exponential growth. Okay, let's look at a completely unrelated example. G of x is 1/2 to the x. Let's make an xy chart again. Let's look, see who A and B are first. A, this number in front, not the number being raised to the exponent, that's the base. The number in front, there's nothing there, so that's just 1. And B, the number that's actually being raised to the exponent is 1/2. Now let's think ahead. Base is less than 1, we're going to have exponential decay. Let's see what happens. If I plug in a 0, 1/2 to the 0 power, anything to the 0 power is 1. Hey, that was A. Right there. That's what A is. A is G of 0. Plug in a 1. 1/2 to the first is a half. Plug in a 2. 1/2 squared. To square a fraction, square the top, square the bottom. Plug in a 3. I get 1/2 to the third. 1 to the third is 1. 2 to the third is 8. Whoa, these numbers look familiar. What about if I plug in some negatives? Negative 1. 1/2 to the negative 1 power. Negative 1 exponent means take your fraction and flip it over. We just get 2. Huh. What about a negative 2? 1/2 to the negative 2 means, flip that over, 2 to the positive 2, that's 4. If I plug in a negative 3, what do you think we're going to get? You're right. If you said 8. Okay, so let's plot all these points. We have the point 0, 1. 1 1/2, we'll just have to eyeball these. 2 1/4, 3 1/8. When x was -1, we go up 2. When x was -2, we were up 4. X was -3, we were up 8. So we get a graph that looks roughly like this. That is not crossing over that x-axis. It's just getting really, really close to the x-axis, but it never touches it. So this graph looks a lot like the graph we graphed a minute ago, this guy, only flipped over. It's rotated around the y-axis. And in fact, that's what's always going on. I could take this guy here, 1/2 to the x, and say, well, that's just 2 to the -1 raised to the x power, because that's what 1/2 is, 2 to the -1. But if I have a power raised to a power, I multiply. I could rewrite this, if I wanted, as 2 to the -x power. So this guy here is really this guy here with an extra negative up in the exponent. And we know what happens. If you multiply your x by a negative, that's a reflection over the y-axis. So this graph is this graph flipped over the x-axis. And in fact, you can think of any of your exponential decay functions as one of your growth functions just flipped over. And that's why we get decay. This is, our base here is less than 1. We're going down. If our base is bigger than 1, we're going up. So if I had y equals 1/3 to the x, that would just be 3 to the x flipped over the y-axis. Okay, let's sketch some graphs. Let's say I wanted to graph h of x is 3 to the x plus 1. Well, I know my basic graph here. I know, we're just drawing a rough sketch here. We know y equals 3 to the x is exponential growth. Here a equals 1, b equals 3. But what about the plus 1? I'll deal with the plus 1 in a minute. This guy passes through the point 0, 1 and is growing. That's y equals 3 to the x. Let's kind of make sure he looks like he's going down here. Now, what's this plus 1 going to do? Is that inside or outside the function? That's outside. So I'm going to take this graph and go up 1. This guy has a horizontal asymptote at y equals 0. I'm going to move everything up 1, so now I'm going to have a new horizontal asymptote instead of y equals 0 at y equals 1. This point that was at 0, 1 is going to go up 1 to 0, 2. And my graph will come through here something like this. Here's h of x is 3 to the x plus 1. Okay, another example like that. Just a quick sketch of this. Forget about the plus 4 for a minute. I know that y equals 2 times 1/3 raised to the x is exponential decay. My base is less than 1. My initial amount is 2. So I have some graph that comes in like this. A is 2, so the y-intercept is the point 0, 2. My base is less than 1, so I have exponential decay. I have a horizontal asymptote, y equals 0, the x-axis. Now I'm going to take everything I just did and scoot it up 4. So I go up, 4 to u. So instead of having a horizontal asymptote at 0, I'll have a horizontal asymptote at y equals 4. We can dot that in. This point that was at 0, 2 is going to go up 4, so he'll now be at 6. And my graph is exponential decay passing through that point and hugging that asymptote I just found. So here's the graph of y equals 2 1/3 to the x plus 4. So it's just graph transformations. That's really all we have to do. Okay, now sometimes somebody will hand us a couple of points and expect us to find the function that passes through these 2 points. So there's a little bit of work to do here. We know our goal is f of x equals a times b to the x. That's our basic function. I need to find a and find b. Well, I'm going to play this game. I'm going to write f of x2 over f of x1, the two different x values, 1 and 3. I'm going to write this ratio 2 different ways. So f of 3 over f of 1, using the x values here. Well, what is f of 3? That's 40. What is f of 1? That's 10. But according to the function f of 3, rewriting this, only now plugging in x equals 3, I get a times b to the third. F of 1 means rewrite this, but plug in x equals 1. So I write this ratio 2 different ways, using the y values that I was given, and using the formula that I know I'm trying to hit. Hey, look what happens here. The a's cancel. I get 40 over 10 is 4 equals, I only have b's left. Whatever's left here, I can solve for b. I have b cubed divided by b to the first. One of the b's cancels. I get b squared. I can solve that for b. Just take the square root of both sides, and we get b equals 2, and we're halfway done. Now I just have to find a. I have to find my initial amount. That's not a. That's not a. If this were a 0, that would be a. A is the y-coordinate of the y-intercept. So this is not the initial amount. That's not a. If I want to find a, I have to plug the b I just found and one of the points back into my formula. So I use f of x equals a times b to the x. Let's plug in, say, the point 110. I know the y value is 10. I don't know a, that's what I'm trying to solve for. I know b because I just found it. And I know x. So I plug in the point 110 and b equals 2. I could have used the other point. I would get the same thing. This I can solve. It looks weird because I've got a times 2 because the 2 is kind of on the wrong side here. But that's just 2 times a. To get rid of the 2, divide by it. We get a equals 5. And now we're done. Just write the function in this form. So we get f of x equals a times b 2 to the x. And I know you're tempted to look at that and say, oh, well, that's 10 to the x. No, it's not. Order of operations. This is 2 raised to the x, then multiplied it by 5. I cannot multiply the 5 and the 2. Okay, that is exponential functions. Exponential functions are related to logarithmic functions, so I'll put some links here to some logarithmic function videos that you can watch as well.